We will draw a PM interaction diagram for a rectangular column section. This is the section. Depth is 500 mm, width is 300 mm. It has six number of 25 mm diameter bars, longitudinal bars. And there is three layers of bars, 1, 2, and 3. First layer is at 60.5 mm from the compression phase, and the total area of steel is 982 mm square. Second layer is at 250 mm, and the area of total steel is 982 mm square in this layer. And the third layer is at 439.5 mm, and the area of steel, total steel in that layer is 982 mm square. Okay. Now, first of all, we will try to know what is a PM interaction. Interaction curve. The PM interaction design curve is a complete graphical representation of the design strength of a uniaxially eccentrically loaded of a column for a given section. Okay, so this is a demo graph. Okay, now each point on the graph, these are different points. Each point on the graph corresponds to ultimate load Pu and the ultimate moment Mu associated for the specific location of the neutral axis. So these are the point which gives us Pu and Mu for a particular depth of neutral axis from the compression phase. Right? Now we will see three types of eccentricity over here. Where eccentricity E is equal to Mu by Pu is equal to infinity, and that means at that point Pu is equal to 0. So Pu is equal to 0, and that is over here, right? Over here, E will be equal to infinity, right? Now, eccentricity E is equal to E balance, that is Mu is equal to Mu balance, and Pu is equal to Pu balance, okay? And that is this point, right? Okay, from this graph, we came to know that eccentricity is found to be at infinity when xu is equal to 142.155 mm. Okay. Okay. In case of columns, when the neutral axis falls within the section, okay, then the design stress strain curve for concrete remains as same as that in case of fluxure. Right? Okay. So here, as in case of closure, when Fy is 415, then X to balance is equal to 0.479 into effective depth. And doing the same, we get X to balance is equal to 210.52 mm over here. So this is how, this is this is the point which we obtain when X to balance is taken as 210.52 mm. Now the third point, that is when eccentricity E is equal to mu by pu is equal to 0, that is mu is equal to 0. Okay, so when eccentricity E is equal to 0, then it will be a case of column under pure compression, and the moment will be equal to 0, and we will get the maximum compression force that the section can carry. Okay, at this time the neutral axis will fall at infinity, right? So this is this point. Okay, so over here the eccentricity E is equal to 0, right? When we join this line, that is from this balance section point to the origin, above that E will be less than E balance, and below that E will be greater than E balance, right? So in this case, we will get a compression failure. What is a compression failure? When E is less than E balance, yielding of the longitudinal steel in tension. Okay, so this is the compression phase. This is the longitudinal steel in tension. Okay, does not in tension does not yielding does not. Okay, yielding of this tensile steel does not take place. Okay, and before that, uh, outermost concrete highly compressed face gets crushed and the concrete phase. So that is a compression failure. Now, when we are below this line, okay, then E will be greater than E balance, and you will get a tension failure. When E is greater than E balance, yielding of the outermost longitudinal steel, okay, this is the outermost longitudinal steel. This will yield first, okay, then successive yielding of other steel bars inside this goes on, and ultimately this highly compressed phase will get crushed and the column will fail. That is tensile failure, right? Okay. So in case of short columns, okay, uh, for finding the balance XU, we take strain at the highly compressed phase as point ultimate strain on the concrete highly compressed phase as 0.0035, and in case of steel we take it as 0.002 plus 0.87 Fi by Es. But if it is a standard column, then the strain in case of steel, that is the outermost steel layer in tension, that is taken as 0.002 only. Okay? So this is the important table where uh, uh, stress corresponding to strain are shown. So which we will be using a number of times for finding uh, the ultimate PU and ultimate MU for the for a particular depth of neutral axis from the compression phase. So let us now draw the PM interaction diagram for this section, right? Okay, so we will use the input first. Fy we have taken as 415, okay, Newton per meter square. Here we are taking as 25 Newton per meter square. The center depth is 500 mm. Press enter. Width is 300 mm. Press enter. First point, we will start with the neutral axis at 142.155. We know at that point the eccentricity is equal to infinity, that is Pu is equal to 0, right? So let's start with that 142.155. Press enter. Okay, total number of steel layers are 3. The first layer that is at 60.5 mm from the compressed phase. Area of steel in that layer is 982 mm square. Second layer is at 250 mm from the compression phase. Area of steel is 982 mm square. And the third steel layer is at 439.5 mm from the compressed phase, compression phase, and the area of steel is 982 mm square. Right. Now let us click finish. Okay. You can see that when the neutral axis falls at 142.155 mm, Pu is equal to 0, right? And over here we can see there will be four forces. Over here there are two forces. One is purple and another one is blue. Purple is due to the compressed design stress strain diagram. Okay, so that we call it as FCC. Okay. FCC is found to be 385.95. Let's see how do we find this. So there will be four forces, one due to this concrete stress strain diagram, another due to this steel layer, third one due to this steel layer, and the fourth one due to this steel layer. Okay. Now, compression force we are taking as positive, tensile force we are going to take it as negative, and anti-clockwise moment about the CG we are going to take it as positive, and clockwise moment about the CG we will take it as negative, right? Right. So how do we get this abscess? So our neutral axis falls within the section, right? So we can use the simple formula that we use in case of flexure, that is FCC is equal to 0.362 FCK XUP. So this is how we find FCC, right? So this is how we get FCC. Now, what is PU? PU is obtained by PU is nothing but addition of all these four forces, right? So FCC is positive because it is under compression, right? Now let's just draw the strain, right? This steel layer is under compression. This is AFC, and this is going to be AFC, right? So this, the force due to this steel is going to be positive. So for finding the force in this steel, first we have to find the strain over here, right? So we know strain over here is 0.0035 because the neutral axis is in the column. When the neutral axis is within the column section, the strain at the compression phase we have to take is 0.0035, and on the tensile phase we have to take is at 0.0035 into d minus xu divided by xu. Right? So this is how we get the strain at the both the phases, right? So knowing the strain over here and over here, you can find the strain which turns out to be 0.002. Okay. Once you know the strain, you can find the stress. Okay. So 0.002 strain falls between uh, these two. So by interpolation, you can find the actual stress corresponding to 0.002 strain, right? So whatever stress which we get from over here, right, that is going to be Fy, right? Now, this is the compression scale. So actual stress Fsc will be equal to Fy, which we get from the table, minus the stress of concrete, that is 0.447 FCK. FCK is 25. So this is how we get the final stress, 316.95 Newton per mm square. Okay, so when you multiply this stress into this area, you get the force due to this steel layer. Similarly, find the strain over here. Okay, the strain is 0.0027. Find the corresponding stress from this table. Okay, so it will be near to this, right? So after you find the actual stress for 0.0027 strain, okay, by doing interpolation, okay. So over here now, whatever value you get from the table, you have to directly use. You don't have to deduct any value for the uh, you don't have to deduct the stress due to uh, concrete in this case because the steel is under tension, and in this case, okay, the concrete is neglected. There is no, we assume that there is no concrete over here. So whatever Fy which we get from the table has to be applied over here without any deduction. Okay. So this is the stress you get. Okay. That is 39.11. Okay, this is taken as negative because this is tensile. So the force, tensile force we are taking as negative, right? So this into this we get the force. Similarly, find the strain over here. The strain is 0.0073. Okay, the corresponding stress is 360.87 because in when the strain is 0.0073, we can see that it is when the strain is greater than 0.0038, okay, or equal to, after that the stress remains constant, it doesn't change. Okay, so that is 361.05. That is the value we will take as average. So the we have taken over here is 360.87. Okay, don't worry. So this stress into this field area gives the force. This is the fourth force. So this is the first force, second force, third force, and fourth force. Now when you add all these forces, you get the ultimate load, that is Pu. Now, how do we get the ultimate moment? Mu. This is Mu, right? So for finding ultimate Mu, we have to take the moments of this force about the CG. So FCC into the CG. So this distance is equal to this distance. Sorry, FCC from left in mm, right? And the distance of FCC, right? Oh yeah, right. So that is 59.13. Okay, perfect. Okay, so when you take the moment of FCC about CG, okay, so this distance minus this distance, that is your lever arm, so that turns out to be 73.66 kilometer, right? Now this is an anti-clockwise moment, so it is positive. Similarly, this force to this steel will also, that is this force, right, into this distance gives you a moment, okay, that is equal to 58.98, okay. So uh, that is also positive because this is anti-clockwise, okay. Now this force, the CG, it acts on the CG, so this will not give any moment, so it is zero, and this force will give an anti-clockwise moment, okay. So into this distance, force is known to us, okay, and distance is also known to us, so we get 67.15 kilonewton meter, and this is plus because we are taking anti-clockwise moment is plus, right? So when you add all this moment, you get the ultimate mu when the neutral axis depth is 142.155, right? So this is how we get a single uh, pu and mu for a particular depth of neutral axis, and which is plotted over here, right? Okay, now let us vary the depth of neutral axis. Say we will take it as uh, 160 mm from the compression phase. Press enter. We can now we can see going to be our complete design stress strain diagram. This is force due to this steel. This is force due to this complete design stress diagram FTC, and these are the forces due to steel layers, right? So over here we get Pu is equal to 76.55, and over here we get 206.96. That is your Mu. Let us plot it on the graph. So this is how this is the second one, right? Now let us take balance XU, right? So that is 210.52 mm, right? Click enter. Okay. Again, click finish. Okay. Concrete stress diagram. This is your balance neutral axis. Okay. And this is your balance PU and balance MU. Okay. Let us plot it on the graph, right? So this is your balance section, right? Now let us take neutral axis equal to 350. Okay. Let us see what happens. Click finish. Okay. So this is the neutral axis. Okay. Now we can see that this steel has come under compression. Okay. Now this steel layer is only under tension. So this is how we get Pu equal to 1298.28 and Mu equal to 196.15. Now we can see as we move, as the neutral axis moves towards infinity, which towards the tension phase, the moment goes on decreasing and the Pu goes on increasing. Right? So let us plot it on the graph. Okay. So more the number of points you take, more a perfect graph you will get, right? Now let us take 450 presenter. Now finish. We can see the concrete stress strain diagram. We can see the strain diagram. Now all the steel layers are under compression because the neutral axis is beyond that, right? And we get Pu is equal to 187.5, 187.45, and Mu 137.65. Okay. So the calculation of stress strain remains the same until this neutral axis is within the cross section. Okay. So let us plot point on the graph. Okay. So this is the point. Now let us take uh, distance of NA equal to 650. Press enter. Now click finish. Okay. So the neutral axis is now outside the column section. So the calculations and the theory changes, right? Now we will see when the neutral axis falls outside the column section, okay, then we can see uh, this is the distance, that is 3 by 7d, and over here the strain will remain 0.002, okay, that will remain constant. This will be our pivot, or you can say the fulcrum point, okay, and this strain will vary between 0.002 and 0.0035, okay. So this is our least strain, and this strain will be 0.0035 minus 0.75 into EU. Okay, we can see the 3D stress diagram. Uh, when we have seen this, that when the neutral axis falls within the column section, then the concrete design stress diagram follows the same as that we have considered in case of flexure. Okay, and, this is a strain diagram. Now, when the neutral axis falls outside the column section, then mm, we can see that this will be our stress design stress strain diagram for concrete, and which we can take as an average, that is xfck. Okay, now you can see over here that at a distance 3 by 7 xu, okay, 3 by 7 d, okay, d is the depth of the column, okay. So this over here, the strain will be constant, or whatever may be the depth of the neutral axis from the compression phase. Over here, the strain will remain 0.002. That will that will be for each and every you can say depth of the neutral axis. Okay, so this is our pivot. This is our pivot point. Uh, so as we move our neutral axis towards infinity, then this minimum least strain will increase and this strain will decrease. And when the neutral axis is found to be at infinitive, then we can see that the strain over whole column cross section will be 0.002. We can see over here. That is the strain over whole column cross section will be 0.002, and then in a falls at infinitive, and the column will be under pure compression. Okay, so when the neutral axis falls outside the cross section, okay, so this will be our design stress diagram for concrete, okay, like this. So we can take an average as xfck with a with a distance g, that is the distance of the center of FCC from the outermost compressed phase. Okay, so for finding x, okay, I have shown the formula over here. A final formula comes to be like this: x is equal to 0.447, 1 minus 4 will be divided by 21. That is okay. So you can study this. Okay, it is very well explained in reference book. There's a design reinforced concrete by Devdas. So you can refer that book also. And A we find as equal to this much, right? So now we will be using this stress diagram. Now, when once the neutral axis falls outside the cross section, then the stress diagram which we used to take, uh, okay, when the neutral axis was inside the cross section will not be valid, and now we will have to follow this stress design stress strain diagram for concrete, right? Okay, so this is how, following the different stress strain diagram as explained just now, we get our PU equal to 2357.22 and MU equal to 53.12. 2, 2. Okay, everything remains the same. Uh, Only in case of steel, uh, the calculation steps for the calculation remains the same, that you have to find the strain at each steel level, and for the corresponding strain you have to find the stress. Okay, but please remember, now all the steels are under compression, so they are going to be ASC. So whatever Fi which we get from this table, okay, for the corresponding strain, has to be reduced by the concrete stress. Okay, that is 0.441 FCK. So this is how we get the final stress. So this final stress into area gives the force, right? Now all the forces are under compression, so all the forces are positive. Okay, so this is also positive, right? So when you add this, you get the ultimate load and moments. Okay, now you can see over here, this uh, blue line indicates the fulcrum point. Okay, the strain over here will remain constant. That's 0.002. Whatever may be the depth of neutral axis, the strain over here will remain constant. This will reduce and this will increase. Right. So this is FCC. This will give an anti-clockwise moment. So it is positive. This will give an anti-clockwise moment, so it is positive. This will give zero moment, so okay. Now this will give a clockwise moment, so that is negative. Okay. So when you add all this moment, you get the ultimate moment. So now let's plot this point. Okay. It comes out to be here, right? Now let us take this as 900. Press enter. Now we can see complex stress diagram. Okay, some here you can see this strain is increasing, this strain is decreasing. Okay, so we get PU, MU, and let us plot it. So it is over here, right? Now let us take as 1200, press enter. Okay, finish. Okay, and you can see the complex stress diagram. It goes somewhere here. You can draw the strain diagram. Okay, this strain is increasing, this is decreasing. You can plot it on the graph. Right? Now we know that when the eccentricity or when the neutral axis is at infinity, that eccentricity is equal to zero, we will get moment equal to zero, and we will get the maximum compression force that the column can carry, Pu. Right? So let us take this as uh, 20, 20 legs. Okay, two, 1, 2, 3, 4, 5, and 6. Okay, so press enter. We take the neutral axis distance from the compression phase as 20 lakhs mm. Okay, finish. Okay, and we can see the strain diagram. Right? Now we can see over here that the strain has turned out to be 0.002 for the whole section, right? So that is what we learned, right? Okay, when neutral axis is at infinity, the strain will be constant over the whole cross section at 0.002, right? That is what we are getting over here, right? 0.002, right? So this is how we can see the moment has turned out to be zero, and the maximum compression force that this uh, section can carry is 2608.84. We can plot this, so we get a point over here. Now, when you draw this, you get a PM interaction curve for this cross section. Okay, so this is how we can develop PN interaction diagram for any column section with any percentage of steel. So this is the basic theory for developing of a PM interaction diagram. Right now, if I now up till now what we have done, we have moved our neutral axis toward this direction, that is toward tensile phase. Now if I move my neutral axis toward compression phase, then the column will uh, become it uh, on the column under tension. Okay, so SB16 has given graph. Okay, which these graphs are continued below this axis, that is for minus pu. Over here the pu is positive. Then uh, then as we move toward the compression phase, you will get a negative pu. So the graph will be extended something like that up to this axis, right? So that will be your graph for a for the column under tension, right? So when you move your neutral axis toward compression phase, you will get the graph for the column under tension, right? When your neutral axis is found to be at this phase, then approximately I think your mu will turn out to be zero, and you will get the ultimate uh, tensile force that the column section can. Okay. So I hope you must have found this video interesting and helpful. Thank you very much.